Hey,
Hey,
good morning.
morning.
We have 7 people here so far. So I'll just give it a couple of minutes to get started.
Okay.
How are your shoes doing?
We'll find out. Maybe there's gonna be like a Walgreens nearby and I can find some other ones.
Awesome. I think we could probably get started. So thank you everyone for joining us. This is another week in the Bitcoin mining summer education series. This week we have Rachel, who is on the mining team, presenting on her research on block headers. So Rachel, I'm going to mute and I'm going to go off video, but I'm here if you need me.
Okay, sounds good. Just give me 1 second. Okay, can you see my screen all right?
Yes.
Okay, cool. So today we're going to try to understand more about the Bitcoin block header. I'm going to give you a brief overview of what the header is. Then we're going to do a network primer, some primitives primers, and then steps on how to mine and how the header fields fit into that process. Some slides get kind of dry, so try to bear with me. All right, the Bitcoin block header. The Bitcoin block header provides a lot of miscellaneous information about transactions in a block. So if Bitcoin's like a living, breathing organism, the block header is the heart of that organism. A block looks like this. We have the block header, and then we have a list of transactions. I think it helps to think of the block header as to be analogous to a document header. So a document header stores a bunch of miscellaneous information like the title, a name, a date, maybe like the current draft and the previous draft. So that way the author can keep their revisions in order and maybe some contact information. So just like a document header has this sort of like administrative information, a block header contains this sort of information that pertains to the transactions in the network. Here's an example of a block header. It's in hexadecimal format, which we will talk about, and it has 6 fields. So before we dive into that, let's go over what happens when someone submits a transaction to the network. Here is the overall flow. It's okay if you can't see everything. We're going to go in step by step. Essentially, we have someone submit a transaction to the network, and then that transaction is propagated through all the nodes. A pool selects transactions, creates the fields that miners need to mine over. Miners mine over those things, send their work back to the pool. The pool processes the work, looks for valid nonces. If it finds one, it creates a new block header, propagates that to the network. And then after a certain number of confirmations, the recipient can spend their Bitcoin. So first step, the sender creates a transaction. Then they send it to their Bitcoin nodes, and their other Bitcoin nodes add the transaction to their mempool. The mempool is a local data structure that each node has, and that is where all of the unconfirmed transactions hang out. It's sort of like a waiting room for unconfirmed transactions. Now the pool goes in and it selects a series of unconfirmed transactions, and it orders them in a data structure called a Merkle tree, which we'll talk about later. And then it collects other data that's pertinent to the block header, as well as the branches of the Merkle tree to send to the miner. Once the miner gets that, they concatenate the fields together to create the block header, and they begin hashing over that header. So that is what's happening in the mining process. They are not hashing over the transactions, they are hashing over the 80-byte block header only. And as they're hashing, they're sending back their submissions to the pool. Not all of these submissions are valid on the network, but it's important that they send back all the submissions to the pool so they can get proper credit for the work that they do. The pool processes the submissions, and then if a nonce is found, it creates a new block and block header. Then it propagates that block to its connected nodes, and those nodes verify it and then add it to their chain. Finally, the recipient gets their transaction and gets all their sats. Again, here's the whole process. Now we're going to do a primitive sprinter. This, I just need to go over like some basic numbering systems and formatting so we can all be on the same page with how to read the block header fields. I apologize if you already know this, but I think it's going to help to get everybody on the same page. But it's not complicated. So I just want to talk about the decimal system. This is a base 10 number system. This is the one we all use and we're all familiar with. We use 0 through 9 to express a full range of integer values. But numbers can be equivalently expressed in any other number system that uses a different base. Two bases that are really helpful in Bitcoin are binary numbers and hexadecimal numbers. Binary numbers are base 2, so we only need 2 values to represent a full range of integers. Those values are 0 and 1. A lot of time you'll see binary numbers prepended with the character B. At the bottom, you see, I've just listed numbers 0 through 4 in their decimal and then in their binary equivalent. So you can see the difference and you can see how much more verbose the binary numbers are. So just doing another example, if you look at the decimal number 4, we write it out with several leading zeros. So 0, 0, 0, 0, 0, 1, 0, 0. The reason we do this is because of how computer memory is laid out. If we just wrote 1, 0, 0, that is totally valid, but computers need to know how much space they need to save to store your number. So you have a bunch of different data types, and you want to just be explicit in the number of spaces the number of digits you can include. Now we're going to move on to hexadecimal number systems. This is base 16. So we have 16 values that represent a full range of integers. That's 0 through 9 and A through F. A lot of times you will prepend hexadecimal numbers with a 0x. As an example is if we have the number 3,735,928,559. In hexadecimal, that is dead beef, DEADBEEF. It's a 4-byte number, and every 2 characters is equivalent to a single byte. So DE is 1 byte, AD is 1 byte, and so on. At the bottom, I have this number in decimal, hexadecimal, and binary, so we can all see how much more verbose the binary is and how succinct the hexadecimal is. And again, like these are all the same numbers, just different ways to represent the same number. One more concept I want to talk about is Indianness. Indianness is just how we format those numbers in computer memory. It sounds kind of complicated, but I think a really good analogy is one that Yuri came up with, and he explained it as in America or in English, we say the number 23, but in Germany, they say the number 3 and 20. So this is totally equivalent. We're all just saying 23. We just say it in opposite order. The etymology of Indianness actually comes from Gulliver's Travels. In it, there is the story of two groups of people, Little Indian and Big Indian. And the Little Indian people, they break their eggs from the bottom of the egg, and the Big Indian people break their eggs from the top of the egg. And they like start fighting and chaos ensues, and it's a whole big thing, even though there is really no difference between like breaking your egg at the bottom or the top. So Indianness in computers, you have a number and you store it in memory. If it's Big Indian, you store the most significant bytes first. And if it's little, you store the least significant bytes first. And so I'm going to explain that in a little bit more detail. Big Indian is what we are all used to. It stores the most significant bytes first. The decimal number 3,735,928,559, written in Big Indian hexadecimal format, again, is dead beef and presented here. This is exactly what we saw on the last slide, exactly what we intuitively would read this as. So Little Indian, it reads the least significant bytes first, and it's not how we intuitively read numbers. So we take the same 3 billion number and we write it in Little Indian hexadecimal format. We get EF, BE, AD, DE. If we took that number and we did not consider Indianness and we just assumed it was Big Indian and we naively just converted that back to decimal, we would get this 4 billion number here, which is incorrect. So while it doesn't matter which Indianness you use, it's very important to stay consistent. Unfortunately, in Bitcoin, there's a lot of inconsistencies in Indianness, so you just need to be really careful. But most of what we're going to be dealing with is Little Indian. And then here's a summary of what we just talked about, just so everyone can see the differences. Okay, so now we're really going to get into it. We're going to talk about the steps to mine and how the header fields fit in with these steps. To rehash, we have 6 fields in the header. We've got a version number, a hash of the previous block header. We have the Merkle root of all the transactions in the block. We have the time that the block is submitted. We have a network encoding of the difficulty target. And we have a nonce, which is the dedicated number that miners update to create a bunch of hashes. Here's the overall process for mining. I know it is a lot, but just like we walked through the transaction submission process, we're gonna step through this one by one to hopefully make it clearer. Just to do a brief summary, we're gonna start the construction of the block. We get a version number, we get the previous hash, we get all the transactions that we wanna include in the block and create a Merkle root from that. We get the current time and the network difficulty. We can concatenate those things to form a message. We choose a nonce. We add the nonce to the end of our message. We hash over that. We ask ourselves, does the resulting number from that hash meet the network difficulty target? So when we hash over the header, all we get is just a number. We just get a number out. And the network difficulty target is just a number. And so in order to say, hey, we have a valid block, the number we get from our header hash has to be less than the number of the network difficulty target. If it's not less, then we're going to choose a new nonce and we're going to hash again and check again. And if it is less than network difficulty target, we have found a valid block and we can propagate that to the network. All right, so let's do this in more detail. So we start construction of the new block, and then we choose a version field. Let's talk about the version field a little bit. It doesn't seem like it is that significant. It's like, okay, just the version of block, whatever, but there's actually a lot that the version field does. It's used by miners to signal readiness for soft fork proposals. Some portions of this field is also used for additional search space, so kind of as like a bonus nonce. And currently the version field is defined in accordance with the BIP9 specification, which we're going to talk about. To give a little context, version 1 started with the Genesis block, and there was no meaningful signaling until 2012. Then Bitcoin Core version 0.7 introduced BIP34, which rendered version 1 blocks to be non-standard and moved us to version 2. What this did, it gave miners a structured way to signal readiness to accept soft fork proposals. This is done via what's called a double threshold switchover mechanism, also called is supermajority. It's kind of a mouthful, but basically it just means there's two thresholds to adopt a new proposal. The first, once a new proposal is active, when blocks are coming in, if 750 of the last 1,000 blocks have signaled readiness to upgrade, then any blocks that are coming in as version 2 but don't comply with the version 2 standard or the soft fork proposal, those are rendered, those are unaccepted. And then after that threshold is hit, we reach the 95% threshold. So 950 blocks out of last 1,000 blocks, if they come in and they signal readiness for the soft fork proposal, then all blocks coming in as version 1 will be unaccepted. In addition to this readiness signaling mechanism, BIP34 also required that version 2 blocks would include the block height as the first item of their script signature in their Coinbase transaction. That's not important to understand, but I just wanted to include this for completeness. There were some problems with BIP34 though. That was the lack of a timeout. So once you started a soft fork proposal, you couldn't really end it. It was just kind of going and going until it kind of got accepted or just never caught on. And then also it would use the entire version field. It would use like an integer value rather than individual bits. And so you couldn't have multiple soft fork proposals going at one time. And BIP9 solved both of these issues. So what BIP9 did is that it gave a soft fork proposal a distinguishing name. It said that a miner would signal readiness by flipping a single bit in the version field, and that bit location is determined by n. And then it also has a start time, which specifies when the selected bit gains its meaning, and it has a timeout. So that if a proposal has not been locked by this timeout, then it will be deemed a failure. By flipping a single bit in the version field, instead of selecting the entire integer field, you can have multiple proposals at one time, like I previously mentioned. And also, bits not being used to signal soft fork readiness can be used as extra search space by the miners in a process called over ASIC boost. So let's look at some examples of how a miner would signal readiness with BIP9. One requirement of BIP9 is that the topmost bits, again in Little Endian, must be 001 in binary or greater. This is highlighted in red up here. So this one bit will always be flipped with BIP9. So let's say that there is a new soft fork proposal. And also an example of a soft fork proposal, just so we're on the same page, is like SegWit or Taproot. So let's say there's a new soft fork proposal coming in, and we're going to call it BIP-in0. And BIP-in0 specifies that the 0th bit needs to be flipped if a miner is ready to accept this proposal. And when I say a bit is flipped, I mean, if a bit is 0 and we make it 1, I just flipped the bit. Or if it's 1 and I make it 0, then I just flipped it. So we're assuming we're all starting with zeros here. So if I'm a miner and I want to say, hey, I'm ready for BIP N0, my Bitcoin client is updated, I'm ready to participate in this soft fork, I will flip the 0th bit to 1. And so instead of having a version number of 200000000, I will now have a version number of 200000001. I also want to give an example of how multiple soft fork proposals can happen at one time. So at the top, I've just repeated the BIP N0 example. And then in the middle here, this represents a second soft fork where I'm going to call it BIP N1, and that is going to require that the first bit be flipped. So here you can see it in red. And then at the bottom, we have a third soft fork proposal called BIP N2. And it requires that the readiness bit be flipped in location 2. And again, you see this at the bottom. So let's say I'm a miner and I'm only ready for BIP N0 and BIP N2, but I'm not ready for BIP N1. BIP 9 specification is really cool because I can signal that. I can only flip the 0th bit and the second bit and leave that first bit at 0. And the network knows that I'm ready for BIP N0 and BIP N2, but I'm not ready for BIP N1. Miners can also use the remaining bits of the version field as extra search space. This is called overt ASIC boost. For a while, miners were just like flipping all the bits randomly, and a bunch of warnings were being generated by Bitcoin clients because Bitcoin clients are unaware that miners are using that for extra search space. So to suppress these warnings, BIP 320 was introduced, and it solved the problem by designating 16 bits specifically for the overt ASIC boost and leaving 13 bits specifically for soft fork proposals. So that gives a miner an extra 2 to the 16 bits of search space with the version field. All right, that was a lot. And now this next field is much simpler. We're going to query the blockchain for the previous block hash. So if we are at block 690473, the second field in the block header is the previous block hash. So that is the block hash of 690472. If you look and see, if you hash this block header, the output is this hash down here, which is included in this later block 690473. So this is actually what makes the chain. The fact that we have the header hash from the previous block in the current block is literally the blockchain. It is what links all of the blocks together. So after we get that, we're going to build our Coinbase transaction and choose transactions from the mempool. So these will be all the transactions that we're going to include in this block. From there, we can calculate the Merkle root. The Merkle tree data structure is really commonly used in multiple fields across computer science. In this case, it's used to cryptographically tie each transaction that is in the transaction block to the block header in a succinct 32 bytes. So this way, instead of including all of the transactions in all of the hashes, we don't have to do that. We can have this 32 byte number that's very succinct, and we can send that in to be hashed in the mining process instead of a huge number of transactions. Just to briefly review the Merkle tree data structure, at the bottom you have this data Each one of these data will be a transaction in the Bitcoin network. So you take data 0, data 1, or transaction 0, transaction 1, hash them together, or hash them individually, and then you take those hashes and then hash them, and you just keep hashing up the tree until you get to a final single hash. And that is the Merkle root hash, which is what is included in the block header. Next, we pick the current time. So the time provides means for the network to determine how fast blocks are being confirmed. That way it can appropriately adjust the difficulty to basically keep block times at about 10 minutes apart. Consensus rules constrain the range of accepted timestamp values to about a 3-hour window. This leaves extra bits that can be used for extra search space, as long as your time is within a 3-hour window. Also, here we're using epoch time, which is just a way to format time. Instead of using like year, month, day, we're actually just using number of seconds. And it's the number of seconds since January 1st, 1979, which is a very common way to express time in computer science. So a valid timestamp must be greater than the median timestamp of the previous 11 blocks. At a confirmation rate of 10 minutes per block, this is 1 hour from the submission time of the candidate block. The timestamp must also be less than network adjusted time plus 2 hours. One unintended consequence of this is that this timestamping system actually makes Bitcoin a really effective timestamping tool. All right, next we're gonna query the chain for the network target difficulty. This field can get a little hairy. So we're just going to touch on it, and then we're going to actually look and see exactly how the encoding happens in a few more slides ahead. But the nbits field encodes the current target threshold in a compact 4-byte field. The resultant block hash must be under the target in order to be considered a valid solution by the network. So again, when we're mining, we just take this block header, we hash it, and that hash is just a number. And we have the network target difficulty, which is again queried from the network, and that is just a number. And as long as the header hash number that we produce is less than the network target difficulty, then we have a valid block. That is the whole point of mining. We're just trying to find a number that is less than the network difficulty. So now we take all these fields and we concatenate them to form a message M. Notice we don't have the nonce here yet. Now we choose a nonce. So the nonce field is incremented in order to create a new hash of the current block with the intention of finding one that meets the current target. It provides 2 to the 32 bits of search space. It plays an essential role in finding a valid block because without the nonce, every single time a miner constructs a block that did not meet the network difficulty, they would have to modify their transaction set, recalculate the Merkle root, rebuild the block header, and rehash. And that is just a lot of unnecessary work. The nonce makes it such that a miner only needs to construct the header candidate once, keeping all the variables constant except for the nonce. The miner will increment the nonce and then rehash the block until either the block hash meets the target difficulty, so they found a valid block, the block becomes stale, a competing miner found a valid block, or they run out of nonce search space. So now we concatenate the nonce with the rest of the header fields. And this is the full 80-byte header that will be hashed over. We take the double SHA-256 hash and we get a block hash. Now we need to ask ourselves, does this number satisfy the network difficulty target? So let's talk a little bit more about the network difficulty target and the nbits field. So the maximum difficulty target is presented here. It's usually used in its truncated form. You can see that it is a very, very, very big number. Let's talk about how that big number is encoded in this 4-byte field. So the first thing you do is you swap the endianness. You separate out the first byte from the remaining bytes. That's called the mantissa or the significand. The mantissa is the part of a floating point number that represents the number of significant digits. It is then multiplied by the base, which in this case is 2, and raised by the exponent to give the value of that number. It's kind of a mouthful, so I have the actual equation typed out here. I think it's a little bit easier. So you see we have the last digits of the n bits at the bottom, and then we multiply it by 2 raised to the power of 8 times the first bit minus 3. I didn't include it in this, but the minus 3, the reason for this is because if you don't subtract 3, you run out of computer memory space because the number is too big, and so you start to lose digits. Okay, so now that we've calculated that, we can compare our block header hash to the network difficulty. And we see in this case, our block header hash that we just calculated is bigger than the network difficulty, so we did not find a valid block. So the answer is no, we did not satisfy the network target. So now we're going to go ahead and choose a new nonce. Here's our new nonce and our new block header. And then here's our new hash. And now this hash is less than the target difficulty we previously calculated. So we have found a valid block and we can propagate it to the network. And that is my presentation.
Rachel, that was great.
Thanks.
It's very, very always fun to learn about how it all works in like the technical part of it. So thank you for doing that. So tomorrow, Rachel will be on Twitter Spaces to answer any questions about her presentation and talk generally about mining. That will be at 9 a.m. So we will see you there. Thanks again, Rachel.
Thank you so much.
Bye.
Bye.